I'm Eric Crable, a technical marketing engineer at Xilinx. Thank you for joining me on this quick sprint through one facet of the SEU solution for UltraScale Plus devices. Xilinx provides a complete SEU solution for UltraScale Plus FPGAs and UltraScale Plus MPSoCs. The SEU advantage of UltraScale Plus devices reduces total cost of ownership by providing reliability, availability, and serviceability. High reliability is achieved with ultra-low SEU rates through device architecture, circuit design, and process innovation. High availability is achieved with rapid error detection and mitigation responses. High serviceability is provided through detailed event reporting and runtime event assessment. UltraScale architecture SEM IP is a key component of the SEU advantage of UltraScale Plus devices. It intelligently manages error detection and mitigation of configuration RAM, driving high availability. It also generates event reports and event assessments for configuration RAM, serving the detailed information about what is taking place, so the system can make informed decisions when exceptional conditions occur. In addition to runtime protection, it also provides error injection capability and diagnostic commands. These are crucial capabilities everyone should use for integration testing. There are a number of ways to integrate the UltraScale architecture SEM IP into a system. Xilinx recommends using the monitor interface, which is a streaming bidirectional exchange of ASCII characters. The monitor interface provides full observability and control of the UltraScale architecture SEM IP. The example design that comes with the UltraScale architecture SEM IP demonstrates connection to the monitor interface with a UART, but you can remove the UART and replace it with anything. For example, a mailbox or a register file, whatever you like for flow-controlled inter-process communication. Today, we're going to leverage the ease of use provided by the UART to integrate the UltraScale architecture SEM IP into an UltraScale Plus MPSoC design through 4 signals. Let's take a look at those 4 signals in detail. The 4 signals are a clock, a serial transmit and receive pair, and a control signal. It can be as simple as that. The clock for the UltraScale architecture SEM IP can come from a variety of sources. While you can put an additional oscillator on your board to provide the clock signal through a user I/O pin, a lower cost solution is to use a clock that already exists in your design. Here, I took advantage of a clock in the PS that is routable into the PL called PL0. There are several such clocks and their frequencies are configurable. PL0 is enabled by default with a default frequency of 100 MHz. You can increase the frequency up to 200 MHz for the UltraScale architecture SEM IP. The serial transmit and receive signals are used for communication between the processing system and the UltraScale architecture SEM IP. The processing system has 2 integrated UARTs called UART0 and UART1, and the associated signals for each UART can be configured to exit the device on physical MIO pins or to enter the programmable logic through internal connections called EMIO. I left UART0 at its default, configured for physical MIO pins, as it's often used for standard I/O in application development and debug. UART1, on the other hand, I changed so that it's routed into the programmable logic, with intent that it will be connected directly to the UART that is part of the UltraScale architecture SEM IP example design. From the processing system perspective, UART1 RX will be used to receive status from the UltraScale architecture SEM IP, and UART1 TX will be used to transmit commands. The 4th signal is used to ensure orderly start of the UltraScale architecture SEM IP. It's a control signal implemented with 1 GPIO. Like the processing system UARTs, GPIO can be configured to route into the programmable logic. The GPIO is used to control a global clock buffer, a buffGCE, in the programmable logic design, so that the clock for the UltraScale architecture SEM IP can be enabled under software control. The default output value of GPIO is 0, so the clock is initially disabled. I'm not assuming the PL0 clock is provided exclusively for use by the UltraScale architecture SEM IP, so I need to provide the control capability rather than relying on software control of PL0. Software control of the clock is required for 2 reasons. The first reason is to ensure the clock provided to the UltraScale architecture SEM IP is disabled until it is known to be in specification, providing ample time for any clock management circuits to lock before allowing the clock to be applied to the UltraScale architecture SEM IP. This requirement is not specific to UltraScale architecture SEM IP in UltraScale plus MPSoCs. It applies to any design that's receiving a clock from a clock management circuit rather than a free-running oscillator. The second reason for software control of the clock is specific to UltraScale plus MPSoCs. The programmable logic configuration RAM, which stores the bit stream of the programmable logic, has a number of access ports, including the Processor Configuration Access Port, or PCAP, in the processing system, and the Internal Configuration Access Port, or ICAP, in the programmable logic. The processing system uses the PCAP to transfer whole and partial bit streams into the programmable logic configuration RAM. UltraScale architecture SEM IP uses the ICAP to access configuration RAM for the purpose of SEU mitigation. The configuration RAM is a single-ported memory system, which means that PCAP and ICAP need to share access to the configuration RAM. In UltraScale plus MPSoCs, the processing system controls which port has access, and it can be changed under software control. During UltraScale plus MPSoC boot, the PCAP has access to the configuration RAM so that the first stage bootloader, or FSBL, can transfer the initial configuration of the programmable logic into the configuration RAM from the boot device. By default, when the FSBL has completed, it leaves the PCAP in control of the configuration RAM, which is the best choice for a default behavior. However, if the design loaded into the programmable logic needs to use the ICAP, the programmable logic design needs to wait until ICAP has access to access the configuration RAM. This is the case with the UltraScale architecture SEM IP. In this design, I use the standard boot sequence without any change to the FSBL. After execution has handed off from FSBL to my application, the bit stream with UltraScale architecture SEM IP will have been loaded in the programmable logic, the PCAP will have access to the configuration RAM, and the clock to the UltraScale architecture SEM IP will be disabled. For orderly start of the UltraScale architecture SEM IP, my application must first transfer access of the configuration RAM from PCAP to ICAP, and then enable the clock to the UltraScale architecture SEM IP. I used Vivado IP Integrator to do the hardware design. You can pause this video to look at the block diagram in detail, but let me quickly touch on key points for each block. The MPSoC block is from the IP library, and I ran block automation to set it up for my board, the ZCU 102. Then I changed the configuration of the GPIO and UART1 to use EMIO, which exposed these ports to the programmable logic. The slice block is used to slice off a bit of the GPIO to control the clock buffer. I used the utility buffer block, configured as a clock buffer with enable, to buffer the PL0 clock signal using the GPIO bit as the enable. The UltraScale soft error mitigation block is also from the IP library. UltraScale Plus device support became available in Vivado 2016.1. You should always check PG187 for the current list of supported devices. If the device you are looking for isn't in the list yet, contact your sales representative to inquire about its support schedule. I configured the block for mitigation and testing with a 100 MHz clock and separately generated the example design for it so that I could copy the 4 RTL files for the example design UART. I added those files to the project and then placed the UART as an RTL block. The UART runs at 115 kilobaud by default, which is convenient because that's also the default for the processing system UARTs. You can increase the rate up to 921 kbaud if reduction in communication latency is of interest. The remainder is just constants and wiring. The constants tie off the unused ports on the UltraScale soft error mitigation block, and the wiring connects the UltraScale soft error mitigation block to the UART block, and the UART block to the MPSoC block. The rest, they say, is just a matter of software. I used System Development Kit to do the software design. You can pause this video to examine the code, but let me quickly touch on what's done here, in what order, and why. At a very high level, I'm showing two things: how to start up the UltraScale architecture SEM IP, and then a simple example of interacting with it. Startup of the UltraScale architecture SEM IP, as described earlier, begins with changing which configuration RAM access port is active. The FSBL left the PCAP active, but I need to change that to make ICAP active. That change is made through the PCAP control register by clearing a bit called PCAP PR. After making that change, the next step is to enable the clock to the UltraScale architecture SEM IP. That change is made through the GPIO control registers DIRM3, OEN3, and Data3. I program the GPIO bit to be an output, enabled, and have a value of logic 1. At that point, UltraScale architecture SEM IP initializes and sends an initialization report before transitioning to the observation state to monitor integrity of configuration RAM. My simple example of interacting with the UltraScale architecture SEM IP uses polling in an infinite loop. It's essentially the software equivalent of two wires bridging between UART1 and UART0 of the processing system. What I'm doing here in software is to move status received from UltraScale architecture SEM IP to standard out, and to move commands received from standard in to UltraScale architecture SEM IP. I'll show you it works in just a moment, but first let me address a question I'm sure you're asking right now, which is how in the world would I apply an infinite polling loop in my design? You wouldn't. What you would do, though, is leverage the capability and features of the processing system UART, which include a receive FIFO and interrupt capability. After the startup code executes, you receive the initialization report for confirmation and then set up an interrupt to respond to data available in the UART receive FIFO. Once the UltraScale architecture SEM IP has transitioned to observation state, it only transmits messages in two scenarios: a reply to a command you sent, or a notification of an exceptional condition. Given the exceptionally low SEU fit of UltraScale Plus devices, virtually all of the time, you simply listen. Let the UART do the listening for you, and upon interrupt, have your interrupt handler inspect the notification for as much information as you care to have and relay it to your system management software. UltraScale architecture SEM IP state changes are announced by strings that start with the letters SC, and similarly, the uncorrectable and essential flag changes are announced by strings that start with FC. Additional event details are provided in the notifications. Please take a look at PG 187 if you want to learn more about their format. I generated a boot image in advance and programmed the ZCU 102 flash so we could jump right into seeing this example work. I attached the board to this computer and also have TerraTerm open using the correct terminal settings. Let me turn the board on. The FSBL prints a simple diagnostic message, and you can see my application also printed a message. My application then started up the UltraScale architecture SEM IP, and I can see the initialization report. It's working. Let's try a test. A correctable single-bit error, which is representative of most SEU. Go idle. Now I want to inject an error in the center word. Now let's turn it loose. You can see it detected and corrected the error. You can run more tests if you want. I've got another video titled SEU Solution Integration Test by Error Injection, which I encourage you to watch if you haven't seen it yet. But this single test proves bidirectional communication is working and my hardware and software are functional. Now you've seen the integration of the SEU solution is easy. The processing system peripherals are standard, built-in UART and GPIO, and you can leverage existing bare metal or OS drivers to access those peripherals. I hope what we just looked at makes you want to try it. This design was for the ZCU 102, but the approach applies to any board with an UltraScale plus MPSoC. The concept can also be applied to Zynq 7000 SoCs and even Xilinx FPGAs with microblaze soft processors. Thanks for spending your time with me.